Hello, everyone. Welcome to my video tutorial for single-cell spatial data analysis. In today's video tutorial, I'm going to show you how to analyze the dataset generated by the MERfish technology. So, MERfish stands for Multiplex Error Robust Fluorescence in situ hybridization. So it is an in situ single-cell spatial genomics technology developed to visualize mRNA expression in a native tissue environment. So for today's tutorial, we just need to load the Giotto package. In this video, I'm going to show you the first part of the data analysis. We will go through the standard Giotto workflow to analyze the MERfish dataset. So the dataset I'm using is the mouse hypothalamic preoptic region tissue. This is a demonstration dataset from the Giotto package. If you want to practice with my code using this dataset, you can download the data from GitHub. Here you can find all the demonstration dataset for the Giotto package. Once you downloaded the data, we can create a Giotto object. We have the expression data in text file, and also we have the cell coordinators in the text file. We can use both expression data and the cell coordinators to create a Giotto object for the MERfish dataset. Let's run. For this dataset, we also have the metadata available. We can load it in the metadata, and we can click the metadata, have a look at the metadata. You can see in the metadata, we have two columns. One column is the original cell types for each cell, and the second column is the layer IDs. Because in this dataset, they took the 12 layers image from the top to the bottom. You can see here is the layer information. So because we know the metadata, now we can add the metadata information into the Giotto object. So first we can have a look at the cell metadata. You can see in the cell metadata at the moment we only have one column. It is the cell ID. And also we can have the feature metadata. You can see again we only have one column. The feature ID, they are the gene names used for in situ hybridization during data connection. You can see we have 161 genes in this dataset. So now we can add the cell layer information into the metadata, and also add the cell type information into the cell metadata. We can have a look at the cell metadata now. You can see we added two more columns into the cell metadata. Now we have the layer ID and also the original cell type information. In this dataset, you can see in total at the moment we have 73,655 cells. So we created the MERfish Giotto object. Now we can go to the second step and process the Giotto object. So first we can have a look at the detected features and the cells information. For data filtration, we can look at the features first. You can see we generated a figure here to show the detected features in each cell, and also we can have a look at the cells. You can see in the plot windows, we have another figure to show the features detected per cell. You can see majority of cells have features detected more than 25. So now we can use the filter combinations function to determine the best threshold for filtering the dataset. Because when we filter the data, the default setting for the expression threshold is 1, so we can use the expression threshold as 1 here. And we want to keep the cells that have at least one feature detected. And we can use a combination to look at the features detected in minimum number of cells. We use 5, 50, and 100. So we can use the combination here to select the best filter threshold. Let's run. You can see here, because we set the expression threshold as 1 and also the minimum detected features per cell as 1, so we just need to look at the features expression in minimum cells. So you can see if we set the minimum number of cells for feature detection as 5, we will filter out around 2 features and 15 cells. If we set the minimum number of cells as 50 or 100, you can see we will filter out more than 7 features and also around 15 cells. So for this dataset analysis, because it is a spatial dataset, we want to keep as many cells as possible, even they don't have expression for the genes that used in this study. So if you look at the online tutorial, they actually set the features detected in minimum cells as 0 and also minimum detected features per cell as 0 as well. So here, I showed you my combination. We can use features detected in minimum cells as 5, minimum detected features per cell as 1. Then we can use this combination to filter the cells. Let's run. You can see down here, with my combination, we removed 15 cells from 73,655 cells. And we removed 2 features. Now we only have 159 features. The online tutorial, they set the both conditions as 0, so they kept all the cells and the features for the analysis. So after filtering the data, now we can normalize the data. Following data normalization, we can add the statistical data into the Giotto object. Let's run. We can have a look at the cell metadata now. You can see we added 3 more columns, the feature numbers, percentage of features, and the total expression for the features in each cell. And we can also have a look at the feature data. You can see we added 5 more columns in the feature data. This column is the total cells that express each gene and the percentage of the cells against the total cells. Here is the total expression, then mean expression, and the detected mean expression. So after we add the statistics, we can adjust the Giotto matrix. This is the last step for data pre-processing. You can see we are going to adjust the normalize the expression values and also adjust the data between different layers to get rid of technical effect. Let's adjust the matrix now. So after this step, we finish the data pre-processing. If we want, we can plot the 2D and 3D image to have a look at the data. First, we can use the spatial plot to look at the data in two-dimensional view. Let's run. You can see here is the image to show the cells in two-dimensional view. Because we have 12 layers in this dataset, it doesn't give you a lot of information. Then we can view the data in three-dimensional. Let's run it again. So you can see we generated a 3D image. If you hold the image and turn it around, you actually can see individual layers. So at the moment, because we didn't cluster the cells, all the cells were shown by one color, the blue color. So next step, in step 3, we can perform dimensional reduction analysis. As I showed you in the standard workflow for the expression data analysis, we can use the calculate highly variable features function to identify highly variable features for PCA analysis. But here we only have 159 genes. So we can skip that step for highly variable genes identification. Here in the run PCA, we set the features to use as null. Then we can use all the available genes, 159 genes, as features to run the principal component analysis. We can run it now. So after PCA, we can use the square plot to select the best PCA number for UMAP analysis. Let's generate the square plot. We can zoom in. You can see in the top image, once the PCA number reaches to 11 and 12, then we will capture the same information with the rest PCs. We can use PC1 to PC12. For the online tutorial, it actually uses the PC8. So we can use the same PC number for UMAP analysis. This will be easier later for me to demonstrate the cell annotation. So let's set the dimensions to use as PC1 to PC8 and run the UMAP analysis. Once we finish the UMAP analysis, we should be able to visualize the cells in 3D view. Let's plot the UMAP in 3D to look at the cells. We can run. You can see now in the 3D image, we can see different cell clusters. But again, you can only see the cell clusters in the same color. Not because we didn't cluster the cells yet. So in next step, we can cluster the cells. First, we can create a shared nearest network. This is the default setting. In this function, you can also set the type as KNN if you want to use the K nearest network analysis. So let's create the shared nearest network for this dataset. Next, we can find the clusters using the latent method. We can run the do latent cluster function. We set the resolution as 0.2. So we identified the cell clusters. Now we can plot the cells in 3D again. You can see we named the latent cluster column as latent 0.2 to 100. So we can count the cells to view the cell clusters in different color according to their cluster number in the Nathan 0.2 200 column. So let's run. So let's zoom in. You can see with the resolution at 0.2, we have 13 cell clusters here. You can identify the cell cluster by different color. Again, you can hold the image and turn it around to see the 3D shape for different cell clusters. So this is the cell clusters in 3D view. We can also visualize the cell clusters on the image. As I said, we have 12 layers in this dataset. We added the layer ID into the metadata. We can have a look at the layer ID information, use the unique function. Let's run. You can see we have 12 layers here from the top to the bottom. The numbers represent the layer information. So now we can visualize the cell clusters on different layers. For demonstration, I selected 4 layers. If you want to see all the layers, you can put all the layers ID here, or you can run this spatial plot 2D function 1 layer by 1 layer. So let's run the spatial plot 2D function to show the cell clusters on 4 layers. I set it here. Let's run. So you can see we generated a new image to show the cell clusters on different layers. Layer ID 210, layer ID 110, layer ID -90, -190. So you can see the cell clusters according to their color on different layers. Okay, this is the first part for MERfish data analysis. In my second part of the analysis, I'm going to show you how to identify the cell markers and the cell type annotation, and also visualize the cell types in 3D view, and also visualize the cell types on different cell layers. So I'm going to stop here for today's demonstration. I hope to see you in my second part of the video tutorial.